Welcome to this deep dive. Today, we're dissecting a really fascinating paper that's trying to push AI's math skills forward.
Yeah, it's a big hurdle, right? Getting these large language models to actually reason through complex math.
Exactly. And, reinforcement learning looks promising, but it often gets stuck, usually because of, the data.
But a data bottleneck, it's a recurring theme.
But this paper introduces something that might just crack it. DeepMath-103K.
Mm-hmm.
So in a nutshell, for those of you maybe just catching the highlights, this is a huge new data set. We're talking 103,000 math problems.
And critically, it's designed to be challenging, very carefully cleaned up, and verifiable.
Verifiable answers, right?
Yeah.
And it's got multiple solution paths for each problem.
Yep, 3 distinct ones generated by another model, R1, all aimed at training better reasoning models, especially using RL.
And the focus is on tough problems, rigorously decontaminated. We'll get into what that means in the early results. Models trained on it seem to be making, pretty significant leaps on standard math benchmarks.
They really are. So the goal today is to unpack DeepMath-103K.
Let's do it. Why is this such a big deal for the AI research community, especially if you're working on mathematical reasoning?
Well, as you said, it comes from researchers at Tencent and Shanghai Jotung University, and they built it specifically to address that data problem holding back AI math reasoners.
Okay, DeepMath-103K. The number alone, 103,000, is impressive. But how is it really different from data sets already out there? People might know math or GSM-8K.
Sure, the scale is one thing, but it's more about the design and the, let's say, quality control that sets it apart. It wasn't just about gathering lots of problems.
The paper stresses challenging, decontaminated, and verifiable. Let's take challenging first. How hard are these problems, really?
They deliberately skewed it towards higher difficulty. About 95,000 problems fall between level 5 and level 10 on the Art of Problem-Solving scale, the AOPS scale.
Ah, okay. For listeners maybe not familiar, AOPS levels get pretty serious, right? Like competition math level.
Exactly. We're talking way beyond basic arithmetic. Levels 5 and up start getting into quite complex territory, needing real reasoning. The idea is you have to push models past just recognizing simple patterns.
You need to force them to develop a deeper understanding.
Precisely. They looked at existing data sets and found DeepMath-103K has a way higher concentration of these genuinely hard problems compared to others.
That makes a lot of sense. No pain, no gain, even for AI models.
Yeah.
Okay, then decontaminated. That's a word that gets thrown around a lot, especially with benchmark leakage concerns.
Yeah.
What did they find when they looked at existing data?
It was actually quite alarming. Their initial check found, surprisingly high contamination rates in the source data they were looking at.
How are we talking?
Potentially up to 90% overlap with some recent benchmarks like AME24 and AMC23. Over 75% with Match 500 in some cases.
90%? Wow. So does that imply, could some benchmark progress we've seen be a bit inflated because models kind of saw the answers beforehand?
That's the worry, definitely. So they put in place a really rigorous 2-stage decontamination process to combat this.
Okay, what did that involve?
First, they used embedding similarity search, representing the meaning of questions numerically to find conceptually similar ones, even if they're worded differently.
Right, going beyond just keyword matching.
Exactly. And then second stage, they used a pretty powerful model, Llama 3.370B Instruct, as a judge. It compared these similar-looking questions to see if they were really the same or just paraphrased.
Well, interesting. Using an LLM to judge potential contamination.
Yeah, and they were clever. They even swapped the question order during comparison to reduce bias in the model's judgment. If there was any significant overlap found, that question got tossed out.
That sounds incredibly thorough, catching conceptual overlaps, not just identical text.
It seems to be. The paper shows examples where this semantic approach caught contamination even when numbers or phrasing were changed quite a bit. This gives us much more confidence that models trained on this dataset are learning general skills, not just memorizing benchmark answers.
Okay, so it's big, it's tough, and it's clean. What about the verifiable part? Why is having a verifiable final answer so important?
The verifiable final answer. That's key, especially if you're interested in using reinforcement learning. Every single problem in DeepMath-103K has one specific correct answer that can be checked automatically.
Which means
you can easily use rule-based reward functions. Think frameworks like RL0. The model tries to solve the problem, you check its final answer against the known correct one. If it matches, positive reward. If not, no reward, or maybe negative.
super straightforward feedback. like right or wrong.
Exactly. It's a very clear binary signal that pushes the model hard towards finding accurate solutions.
Okay, that clicks for RL. But you also mentioned it has multiple solution paths for each problem. How does that fit in?
Yeah, that's another really smart design feature. For every problem, they didn't just get the answer, they generated 3 different distinct step-by-step solutions using the DeepSeek R1 model.
3 ways to solve the same problem. What's the benefit there?
It opens up a lot more possibilities for training, actually, beyond just RL.
Like what?
Well, think about standard supervised fine-tuning, SFT. Instead of just learning from one example solution, the model sees 3 different valid strategies. That should help it generalize better.
Exposure to more ways of thinking, basically.
Right. And it's great for model distillation, too. You can use a bigger teacher model that understands these multiple paths to train a smaller student model more effectively.
Richer guidance.
And also for training reward models themselves. You can teach a separate model to tell the difference between good and bad reasoning steps by showing it these different valid approaches versus maybe flawed ones.
Got it. So DeepMath-103K isn't just an RL dataset. It sounds quite versatile for different training approaches. And topic-wise, it covers a lot of ground.
Oh, absolutely. The topical range is broad. They used a classification system, and it covers everything from pre-algebra basics right up to advanced calculus, number theory, abstract algebra, differential equations, geometry, the works.
Trying to build a well-rounded mathematical AI.
That's the goal. Supporting more general mathematical reasoning, not just specializing in one narrow area.
Okay, putting together something like this, 103K problems, cleaning them meticulously, generating multiple solutions, that must have been a huge effort.
Massive. They mentioned the costs in the paper, something like $138,000 just in GPT-4o API calls, plus around 127,000 H20 GPU hours for the whole curation process.
Wow. Okay, that's a serious investment. It definitely highlights their commitment to quality here.
It really does. It wasn't a trivial undertaking.
All right, so we understand the what and the why behind DeepMath-103K, but the million-dollar question for researchers listening is, does it actually work? Do models trained on it perform better?
And that's where the empirical results come in. They trained several models, including one they call DeepMath-0. That's the one using RL0 specifically with this data set.
And tested them against?
Against a whole suite of tough math benchmarks. Math 500, AIM, AMC, Minerva Math, Olympiad Bench. Basically, the standard challenging test beds.
And the results? Were they good?
They were quite compelling, yes. Across the board, models trained using DeepMath-103K showed significant jumps in performance compared to baselines, and even compared to models trained using other RL datasets.
Even just using it for supervised fine-tuning helped?
Yes, simply fine-tuning a base model on DeepMath-103K gave a substantial boost, and using all 3 solution paths during that fine-tuning improved things even further.
But the RL's results, especially for DeepMath-0, must be the main validation, given the verifiable answer design.
Absolutely. DeepMath-0 consistently outperformed other RL-trained models on all the benchmarks they tried. It even hit state-of-the-art results in several categories for models of its size.
Okay, that's strong validation. It suggests the combination of this specific dataset design, challenging, clean, verifiable, with that rule-based RL approach, really works well.
It seems to be a very effective combination, yes.
Did they look inside the models? Like, how are they solving the problems differently after training on this data?
They did. One interesting observation was that the models trained with RL0 on DeepMath-103K tended to produce much longer, more detailed reasoning steps, especially on the harder problems.
Longer solutions. Does that automatically mean better?
Not necessarily on its own, but it suggests the model isn't just jumping to an answer. It implies more step-by-step derivation and potentially more complex reasoning chains are being formed.
And they also looked for specific cognitive behaviors. What does that mean?
Yeah, they used methods from some earlier research to track how often the model exhibited certain useful problem-solving strategies during training. Things like breaking problems into sub-goals, verifying its own intermediate steps, backtracking if it hit a dead end or made a mistake, and even enumerating possibilities systematically.
And did training on DeepMath-103K encourage those behaviors?
They found a clear increase in the frequency of all these beneficial behaviors as the RL0 training progressed on this dataset. It strongly suggests the data is pushing the model towards more structured, robust, almost human-like ways of tackling the problem.
Wow, that is fascinating. So the dataset itself seems to be shaping how the AI learns to think mathematically.
It really appears that way. And the best part, they're releasing DeepMath-103K publicly.
Oh, that's huge for the community.
Absolutely. It directly tackles that data quality and quantity issue we talked about and could really help accelerate progress for everyone working on AI reasoning.
Okay, so let's quickly recap the big strengths here. DeepMath-103K, huge scale, 103,000 problems, strong focus on difficulty, mostly that level 5-9 AOPS range.
Right, challenging stuff.
Verifiable final answers, crucial for rule-based RL like RL0. 3 distinct R1-generated solution paths per problem, adding versatility.
Yep, good for SFT, distillation, reward models.
Broad topic coverage, pre-algebra to advanced calculus, and critically, that rigorous 2-stage decontamination.
Can't forget that clean data is key.
And this design supports lots of training methods: SFT, distillation, RL0, reward modeling.
Making it a really valuable resource no matter your preferred training approach.
And the proof is in the pudding, right?
Yeah.
The empirical results show significant performance gains on tough benchmarks, state-of-the-art in some cases, for DeepMath 0.
Plus those encouraging signs about reasoning length and the emergence of those beneficial cognitive behaviors, sub-goal setting, verification, backtracking.
Yeah, that's really promising stuff.
It truly is. DeepMath-103K hits that data bottleneck head-on. And releasing it publicly, especially after that significant investment they made, is a major contribution.
So maybe a final thought here for you to chew on. DeepMath-103K isn't just providing data. It feels like it's setting a new standard, a standard for rigor, quality, verifiability in data sets designed for complex AI reasoning.
That's a good point.
And if this level of meticulous curation works so well for math, well, it makes you wonder, doesn't it? How could similar approaches creating really challenging, clean, verifiably solvable data sets accelerate progress in other really complex AI fields? You know, beyond just math. Something to think about. Thanks for joining us for this deep dive.